Un honor otra vez y un placer, por supuesto, presentar al profesor Hewish y simplemente que estar en el mismo teatro durante la semana con dos personas que han descubierto los temas donde yo he trabajado durante toda mi vida es muy emocionante y seguro que no sería muy difícil para Anthony Hewish darnos el sentido del interés y del descubrimiento sobre el tema de los pulsares. Es la mejor persona que existe para hablar del tema, con lo cual estamos todos privilegiados. Okay, Tony, go ahead.
Good evening. I'm sorry that I cannot speak to you in Spanish, but there's a good reason for that. In 1939, I was learning Spanish at school, but my Spanish teacher was called up into the army, and at that time, no one else could teach Spanish at the school, and in a few years, anyway, we were all very busy doing other things, and so I'm sorry I never had time to get back to Spanish again. But I do wish I could speak to you because it is such a beautiful language. I would like to begin my talk by showing you one of the most famous objects in astronomy. What you see there is the famous Crab Nebula. That is the result of a star which exploded in the year 1054. And this is a more recent photograph taken around 900 years later. But when that star exploded, Oriental astronomers were able to see the star in daylight for several weeks before it faded. So it was a very prominent object in the sky. It's still a prominent object now. And it plays a central role in my subject for the lecture tonight. Certain stars, especially the heavy stars, when the nuclear fuel runs out, then of course there's no more heat generated inside the star, and gravity must tend to compress the star inwards. The force of gravity on a stellar scale can be enormous, and it has effects on the interior of the star, which I'll go into in more detail later on in the talk. But the moment the pressure, internal pressure generated by the nuclear fusion reaction begins to run low, then gravity simply squeezes the star, and ultimately, for a really heavy star, the final collapse can be explosively fast. It's an implosion which releases huge amounts of energy and results in the kind of picture you see here. Now, the gas of the expansion.
Pues esta es la nebulosa del cangrejo, llamado así por su forma, que algunas personas pueden ver como un cangrejo. Y es el resultado de una explosión de una supernova que se observó de la Tierra en el año 1054, sobre todo por los astrónomos chinos, y durante varias semanas una estrella nueva apareció en el cielo. Las supernovas son el resultado de una fase final y dramática en la vida de una estrella masiva, una estrella muchas veces más masiva que el Sol, que se explota porque falta de hidrógeno en su centro da lugar a un colapso gravitatorio. La gravedad no es capaz de sostener la estrella, que da una implosión y se explota y deja lugar a esta.
From the speed at which the gas is now expanding, you can determine the point from which the explosion occurred, and you can identify what was left from the original star. And if you can just see at the end of that arrow, there is a pair of stars, two close together in the middle of that nebula, and it is the bottom left-hand star, which has long been thought to be the origin of the explosion.
Una imagen más grande donde se puede ver la estrella en el centro. Hay dos estrellas, la estrella donde aparece la flecha, el punto de la flecha se cree que es la estrella que dio lugar a la explosión.
In 1968, it was discovered that that central star was flashing on and off at high speed. If we take a closer look at the center, you see within the rectangle the two stars I mentioned, and it is the bottom left-hand star which was believed to be the origin of the explosion. And on the right, you see a stroboscopic photograph, effectively taken at 1 millisecond intervals, which shows that that star is flashing on and off 30 times a second, roughly.
Pues la imagen en el centro son las dos estrellas que se ven en el centro de la nebulosa, y la serie de imágenes es una serie tomada con intervalos de 1 milisegundo, la milésima de un segundo, y que se nota que hay una de las estrellas que está variando muy rápidamente su brillo, y esto está pulsando a 30 veces por segundo.
This is what we call a pulsar, and it is one of the few pulsars that you can see by means of their optical light. In general, pulsars are detectable by radio emission rather than optical emission, and here you see the shape of that emitted pulse, which consists of a double peak, and that repeats roughly 30 times a second, with an interval between the pulses of 33 milliseconds. And there you see, in that particular case, the pulsar emits radiation all the way from long radio wavelengths, TV wavelengths, right up to X-rays.
Este pulso es uno de los pocos que se pueden detectar en banda óptica, pero la mayoría, y esa incluida, emite en ondas radio. Este diagrama muestra que emite un pico doble cada 30 veces por segundo. Este pico se ve en rayos X, óptico, ondas radio, las mismas ondas que con la TV también.
The behavior can be explained if we suppose that the star is behaving like a lighthouse. It produces beams of radiation, shown yellow there, which are well offset from the rotation axis. So as the star spins, the beam flashes around in the sky, and if you are aligned suitably, then you will observe flashes for each rotation of the star.
Es como un faro en el espacio, gira muy rápidamente. El haz sale con un ángulo, el haz de luz sale un ángulo con el eje de rotación. Cada vez que el haz pasa a través de nuestra línea de visión, vemos un pulso. Eso ocurre 30 veces por segundo.
This is much more recent image taken in X-rays from the Chandra X-ray satellite and X-ray telescope, and what you see here is the pulsar optically is in the center here. This is surrounding cloud of hot electron gas I think it's hard not to see the rotation almost directly in an image of this sort. The rotation axis would be along here. It is like a firework, a celestial firework, and this gas is thrown off, apparently by the rotation, and is a very convincing demonstration that the model, the lighthouse model, must be correct.
Esa es una imagen en rayos X, hecha de un satélite de rayos X que detecta rayos X, y se nota que hay un eje de rotación, se ve directamente, y se intuye la rotación, da un sentido de rotación rápida. El gas está echada por el pulsar y gira muy rápidamente. Esta imagen da la prueba viva del modelo del faro.
The star which rotates, the pulsar, has to be a very special star because most stars, if you spin them, will fly to pieces because they are not held together sufficiently strongly by gravitation. It has to be a star we call a neutron star. That's to say, it is a star which is compressed by gravity until you contain the mass of a star like the Sun, somewhat heavier, in fact, than the Sun, squashed by gravitation into a sphere which is approximately 20 kilometers in diameter.
Una estrella que gira tan rápidamente, una estrella de materia normal, no podría seguir así, porque la gravedad no sería tan fuerte y se desintegraría por su propia velocidad de rotación. Tiene que consistir en una materia muy densa, y de hecho un pulsar es una estrella de neutrones que consiste en materia muy densa, tiene la masa de una estrella como el Sol, un poco más grande incluso, comprimida en un espacio de unos pocos kilómetros de diámetro.
Now you might ask, how was it that astronomers discovered that rapid flashing of the star inside the Crab Nebula? Well, 1968 was just shortly after we made the discovery of radio-emitting pulsars in Cambridge, which started the whole field I shall be talking about in my lecture. And I'd just like to say a few words about how we actually discovered these remarkable pulsars using a radio telescope in Cambridge. If you turn the clock back to the 1960s, there was a great interest in radio galaxies, galaxies which emit radio waves, and a particular interest in a type of radio-emitting galaxy that we called a quasar. Quasars were exciting because enormous energy was produced in a tiny, compact core within the galaxy, and this immense energy from a small volume in a galaxy caused them to look almost like stars rather than galaxies in the sky. But it was not clear immediately because we had no technology then to obtain good images, radio images of galaxies. So it was very hard to know amongst the 300 or 400 radio galaxies that had been detected which ones were quasars.
Surge la pregunta, ¿cómo los astrónomos encontraron el pulsar de la nebulosa del Cangrejo? Antes de hablar directamente de eso, voy a hablar de el primer descubrimiento del primer pulsar que dio lugar a todo lo demás. Y el primer pulsar se descubrió en Cambridge utilizando un telescopio diseñado no para buscar pulsares, obviamente, porque nadie sabía que existían, sino para buscar cuásares. Un cuásar es el núcleo de una galaxia que emite una cantidad enorme de energía por unidad de tiempo, y entonces era muy difícil, tenía mucho interés, pero muy difícil distinguir cuásares de las demás galaxias. ¿Por qué? Porque no se podía hacer imagen. Y un cuásar es una cosa puntual como una estrella, una galaxia es grande, pero no se podía distinguir así, tenía que encontrar un método para distinguir.
I designed a radio telescope to distinguish which of the galaxies that were detectable were quasars, using a phenomenon we had discovered 2 or 3 years earlier, which is that quasars twinkled. They had a fluctuating intensity which was caused by a wind, a solar wind as we call it, hot gas expanding from the sun in all directions, fills the space within our solar system. And as we look out through this cloud of expanding solar wind, fluctuations in the wind and the density cause very compact galaxies like the quasars to scintillate like stars. They twinkle, but the ordinary radio galaxies do not.
El principio de operación de este telescopio fue detectar el centelleo de los cuásares, que tal y como es la diferencia entre una estrella y un planeta, la estrella varía de densidad, fluctúa por efecto atmosférico, hay un efecto, y en un planeta no porque tiene un tamaño finito, pues hay el mismo efecto analógico ocurre con los cuásares y las galaxias. El espacio interplanetario, es un tipo de atmósfera local de nuestro sistema solar, causa que los cuásares, que son fuentes puntuales, centelleen y las galaxias no, y así se pueden distinguir.
As you can see, it's unlike what one expects a radio telescope to be. This is because the twinkling phenomenon caused by the solar wind is best observed at a long radio wavelength, at a low radio frequency. And I had to design the telescope, therefore, to work at roughly VHF frequencies, much lower frequencies than you would normally use in radio astronomy. And in order to use the twinkling to measure size, I needed to observe the sources many times during the year so that they were viewed with my telescope at different angles relative to the sun. So I needed a telescope that operated at a long wavelength, a low radio frequency, and I needed to make repeated measurements in order to measure the angular size, which really would confirm that I had quasars and not radio galaxies, ultimately.
Pues este telescopio no se parece a un telescopio, se parece más a una granja. Y la razón es porque tenía que utilizar una longitud de onda mucho más larga que lo normal, que no necesita una superficie continua, sino hilos así. Y tenía que observar varias veces al año para así hacer variar el ángulo entre el cuásar y el Sol, porque así se puede medir el diámetro y así confirmar si es un cuásar o no.
It is really a collection of a large number of fairly simple radio antennas. These posts support dipole radio antennas, not unlike TV antennas, and in this large field, which we fill the field of about 2 hectares with over 1,000 dipoles, and with that system we were able to observe approximately 800 radio galaxies each week.
Realmente es un telescopio compuesto de antenas dipolares, poco como antenas de TV, y allí es un agro de how many hectares? 2 hectáreas, y con esto podían observar en una semana 800 galaxias de tipo radiogalaxias con esta antena.
We began a sky survey which was designed to run for about 12 months, in which we observed the whole sky once per week. I should have said before that the rotation of the Earth causes the beam of the telescope to sweep over the sky, so it is essentially for astronomers you would call this a meridian transit telescope. We observe galaxies as they cross the meridian transit and simply observe continuously.
Bueno, para barrer el cosmos, eso está un telescopio obviamente fijo en la Tierra, con lo cual se barre automáticamente con la rotación de la Tierra. Es un telescopio de tránsito meridional en términos técnicos, y así puedes ver muchas galaxias por unidad de tiempo utilizando la rotación de la Tierra.
I had a graduate student who came to work with me, and her job was to analyze the data from this telescope, and it must have been around August 1967 when she showed me a record which was rather unexpected. Along the top, you see the normal radio telescope output. We were looking literally for every twinkling source we could see as time proceeded.
En agosto de 1967, una estudiante de tesis doctoral trabajando con el profesor Hewish le informó de estos resultados. Estaban buscando cualquier fuente mostrando centellas, y esto parece una cosa un poco curiosa. Ella le llamó la atención a la presencia de esta fuente.
Now, on the top recording there, you see the steady output. You see the output from the telescope, and here you see some fluctuating signals, which were exactly the sort of signals we would expect from a quasar showing this twinkling phenomenon. But the problem with that recording is that we are getting a large amount of scintillation at a time when it simply would not have been expected, because scintillation is strongest when you are observing a source not too far away in angle from the sun. And this was happening around midnight when we were looking in the anti-solar direction.
Pues lo que llamó mucho la atención, la variación de intensidad, el aparente centelleo de la fuente, muy curiosa, porque se supone que el centelleo se maximiza con un ángulo de observación cerca del Sol para pasar por el viento solar. Pero esta observación ocurrió cerca de medianoche, cuando el telescopio estaba mirando en la dirección opuesta.
Well, I was curious, very curious about this signal, because it was quite possible in my mind that we were detecting not a radio galaxy, but something more like our sun, but at a much greater distance. We call these flare stars, and there are stars. The sun is a radio flaring star. It sometimes emits a lot of energy at radio wavelengths, and only for a few days perhaps, and then it will go quiet again. And it seemed to me quite possible that we were picking up something like that, but at at a much greater distance.
Su primer pensamiento es que habían detectado una estrella fulgurante. Las estrellas emiten a veces, como el Sol, brotes de partículas, a su vez que emiten brotes de ondas radio. Y pensaba que a lo mejor eso era una cosa como el Sol, pero mucho más fuerte, a una distancia más grande.
In order to make a closer inspection of this strange signal, it was necessary to use a faster chart speed and a more sensitive recorder. Remember, we're talking here about astronomy as it was in the 1960s. We had no digital recording system, no computers attached to this system at all. It was essentially a manually operated instrument with visual analysis of the data. But we set up a much faster recording system because I wanted to see just what was the character of these signals. Were they like the kind of signals we get from the sun? We had a lot of experience by then of what the solar signals would look like at a much greater distance. The first successful recording was made in 27th of November 1967, and to our amazement, the signal was nothing like an astronomical signal at all. It was a series of regularly spaced flashes of radiation coming at intervals of about 1.3 of a second.
Para poder discernir mejor la naturaleza de la señal, organizaron un sistema más sensible a variaciones rápidas en el tiempo y un papel que salió mucho más rápido de la máquina de grabar. Ten en cuenta, era en el año 67, tiempos prehistóricos, cuando no había ni ordenadores en los equipos, todo se hizo así. Tenía mucha experiencia con el Sol y el profesor Hewish sabía lo que estaba buscando, y a su asombro, en vez de ver el tipo de señal ocasional, vio una señal muy regular, con intervalos de 1,3 segundos entre los pulsos.
By careful timing of those pulses, I was able to confirm that the signal was keeping time accurately to a millionth of a second each day. It was a very, very good clock. And by various other experiments, which I won't go into the details, we were able to determine that the source emitting these signals could not be larger than a small planet, only a few 2,000 or 3,000 kilometers in diameter, and also that it was at a distance of approximately 100 light years. It was situated out amongst the nearby stars. And because it looked so absolutely artificial, the simplest explanation, which really rather worried us, was that it was an intelligence contacting us.
Sí, empezó a analizar con mucho más cuidado y cronometrar bien la señal. Notó que era un reloj con una regularidad impresionante, que no varía más de una millonésima parte de un segundo en un día. Después, con instrumentos que no puede describir en detalle, determinó dos cosas: que provino de un objeto realmente pequeño, del tamaño de un planeta o menos, o menor, y que vino de una distancia de alrededor de 100 años luz de distancia en el espacio de las estrellas. Y, bueno, que podía ser, muy probablemente, una inteligencia extraterrestre intentando ponerse en contacto con nosotros.
In order to check further whether perhaps we really were receiving intelligence, I realized that because the pulses were so accurate, I could use the pulsar clock effect to determine whether the source sending the signal was actually in orbit about some other star. If you have intelligence, it has to be on a planet, it has to be receiving energy from some other sun elsewhere, and so life, if it exists, will be in a planetary orbit. And I realized that with the pulsing so regular, we could detect whether the source was in fact in a planetary orbit. In physics we call this the Doppler effect. If the source in orbit was moving towards the Earth, then the pulses would be closer together. If it is moving away from the Earth, the pulses would be further apart. By careful measurements over a period of time, I decided it would be possible to detect, if such existed, a planetary orbit. And for about a month, I carried out those observations each day. It meant going to the observatory regularly when the source was in transit. And my wife will remember that on December the 25th, which is a very important day in England, I disappeared from our family meal table. I had to go to the observatory to take a measurement to see where the pulses were on that particular day. But after 1 month, there was no detector motion, and with some relief, I have to say, I at least dismissed the idea that we were dealing with intelligence, and so we had to look for some other explanation.
Pues una forma de distinguir entre un origen de vida inteligente o no es ver si la señal proviene de un planeta, porque se supone, con bastante racionalidad, que la vida tiene que existir en un planeta, en órbita alrededor de una estrella que le da su energía. Y entonces, midiendo con mucho cuidado el intervalo de tiempo entre los pulsos, se puede ver si hay un cambio de velocidad hacia nosotros y hacia afuera de la fuente. Es el efecto famoso, el efecto Doppler. Y después de un mes, él determinó que no había tal efecto en este caso. Da la anécdota de tenía que medir todos los días, y un día fue el 25 de diciembre, y se ausentó de la mesa familiar en aquel día, al disgusto parcial de su esposa, que está aquí, pero al final él determinó que no vino de un planeta, entonces no provino de vida.
When we published these results, the results of this discovery, in February of 1968, I thought that the most likely explanation was that we were dealing with a neutron star, which I'll mention more detail in a moment, but one of these highly compressed stars, about 20 kilometers in diameter, and my assumption was that it was the vibrations of the star which were causing the pulsing signal, which was a model which later was abandoned in favor of the rotating lighthouse. But in fact, this was the first detection of a neutron star.
Pues antes el anuncio, la publicación del descubrimiento, ya estaba muy convencido que se trató de una estrella de neutrones, este tipo de estrella muy compacta, pero él pensaba posiblemente en una estrella de neutrones en pulsación para causar los pulsos. Más tarde resultó que esta teoría se abandonó en favor de una estrella de neutrones en rotación. Sin embargo, el primer pulsar fue de todas formas la primera estrella de neutrones.
I'd now like to mention some very simple physics so that you understand how a neutron star can exist. If we consider the structure of a normal solid, then we have atoms in which I represent rather crudely here the atomic nucleus in red, surrounded by orbiting electrons, which I show in blue. And in a normal solid, like we have on the Earth, the atoms are pressed together until the electron orbits begin to interact. And at that point, we have a solid, and it becomes difficult to compress it further. But of course, gravity under astronomical, in the astronomical regime, can be an enormous force, and it can compress matter almost indefinitely. And if you just imagine what must happen to matter as you squeeze it, then what happens is that it begins to change its structure altogether. The thing that is hard to realize when we are surrounded by solids, like pieces of iron or concrete, is really how much empty space exists within ordinary atoms that we know so well on the Earth. If you were to draw an atom, if we were to make a model of an atom to scale, and the nucleus was the size of a tennis ball, then the orbiting electrons would be particles which were moving away from the tennis ball, moving around over a size of a small city like Almería.
Bueno, para entender cómo son las estrellas compactas, habrá que entender un poco sobre la estructura de la materia. Nuestros átomos normales, la estructura de todo lo que hay aquí, tienen un núcleo muy pesado, muy compacto, y electrones alrededor. Para dar una idea de la escala, si un núcleo tuviera el tamaño de una pelota de tenis, los electrones se encontrarían alrededor a distancia del borde de la ciudad de Almería. Eso implica que un átomo normal es casi totalmente vacío, casi no hay nada, a pesar del sentido de solidez que nos da.
Now, it's simple physics that particles can sometimes be regarded as a wave and sometimes as a particle. We have the wave-particle duality, as we call it in physics. And the wavelength, the quantum wavelength of electrons in atoms is, roughly speaking, the separation of the atoms in the solid material. If you squash a material, you have to decrease the electron-particle wavelength. So as you squeeze this into a smaller volume, the electron wavelength gets shorter. This means that the energy, the actual energy of the electrons must increase according to this simple relation here, first derived by Planck. The energy varies inversely as the square of the particle wavelength, and so the electron, as the electron energy rises, the atomic structure is destroyed. The electrons have so much energy that they can move freely anywhere, and we call this a degenerate material.
Pues hay que tener en cuenta el modelo cuántico de cómo es la materia. La materia tiene algún aspecto de partícula, otro aspecto de onda. Es la dualidad entre partícula y onda. No hace falta entender muy bien esto, salvo que decir lo siguiente. Un electrón tiene una longitud de onda característica. Al comprimir la materia, esta longitud de onda decrece, pero a la vez la energía del electrón sube. Las leyes de mecánica cuántica son así, esa es la fórmula. La energía del electrón va inversamente proporcional a la longitud cuadrada, esta longitud cuadrada. Eso no importa tampoco, salvo para decir que al comprimir los electrones se sueltan de los átomos y la estructura de la materia cambia, se llama materia degenerada, y es mucho más densa que la materia normal.
If you go on compressing matter, then ultimately you reach the state where the matter has almost combined, the electrons and protons have almost totally combined to form a new particle, the neutron, which is uncharged. You get the reaction where a proton and an electron will convert to a neutron and a neutron. neutrino, which I won't discuss more, but if you squeeze effectively electrons and protons, positive and negative charged particles, hard enough, they will turn into neutrons. This is simply because the energy requirements, nature always tries to find a state of lowest energy to be in equilibrium, and it's preferable in a highly compressed state for protons and electrons to combine to form neutrons. This is exactly the reverse of what happens at low pressure in a physics lab, where if you make neutrons, they rapidly decay. They turn, it's a radioactive reaction, they decay into electrons and protons. At high pressure, the reverse takes place.
En el centro de una estrella muy compacta, la fuerza de gravedad es mucho más alta que aquí, muchísimo más alta. Y como resultado, los protones y electrones que hay se combinan para formar neutrones. En nuestro entorno de baja presión va al revés. Si hay un neutrón suelto, automáticamente dentro de 15 minutos se separa automáticamente y produce un electrón y un protón. Pero una estrella de neutrones al revés. Entonces todas las estrellas se forman de estos neutrones.
It's extremely hard to visualize what neutron material would be like. This closely packed neutrons material would have a density so that you could put 100 million tons into a cubic centimeter. That's to say, a teaspoon of this material would weigh roughly 100 million tons. It's almost impossible to visualize. But the force of gravity, when a star collapses, is sufficient to create material, neutron material of this sort. And it is this sudden collapse to the highly compressed state which occurs at the heart of a supernova explosion, when gravity is sufficient to cause this collapse, and the energy released, mostly in the form of those neutrinos, but also gravitational energy due to the infall. And that is how neutron matter is created, and that is how neutron stars are formed. And it was postulated, as soon after the neutron particle was discovered in the early 1930s, that neutron stars could exist and that they would be formed in supernova explosions. That was the theory, but no one realized that the resulting neutron star would be ultimately detectable as a pulsar.
La materia de una estrella de neutrones es muy densa. Una cucharadita pesa más de 100 millones de toneladas. Es casi imposible de imaginar. Y eso se forma por la compresión enorme hacia el centro del resto central de la estrella, cuyas capas exteriores se explotan como supernova. La implosión del centro da a formar la estrella de neutrones. En los años 30, cuando el neutrón se descubrió por primera vez, físicos teóricos, habían predicho la posible existencia de estrellas de neutrones, pero nadie imaginaba que se podía al final detectar una estrella de neutrones mediante su fenómeno de pulsación, de ser un pulsar.
So it was our discovery of the radio pulsar which caused observers to look very closely at the Crab Nebula. And a radio pulsar, this was not a Cambridge discovery, this was a discovery in the United States, that there was a radio pulsar inside the Crab Nebula, which caused the optical observers with their telescope to look at that central star, which was thought to be the remnant of the explosion, to see if it was a pulsar, and you saw the result, which was that optical flashing. And so this confirmed the neutron star idea very, 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 very convincingly.
Pues después de su descubrimiento del pulsar en Cambridge, los astrónomos viraron y miraron a la nebulosa del Cangrejo encontraron un pulsar pulsando en ondas radio ahí dentro, y después astrónomos ópticos, en un descubrimiento dramático, encontraron que ese mismo pulsar emite pulsas también en ondas visibles, en luz visible, con lo cual todo se confirmó de forma muy elegante la teoría de la estrella de neutrones.
This illustration now shows you roughly what we think a neutron star would be like. It is not just simply a sphere of neutrons, because there is a huge variation of pressure from the outside to the inside. And theoretically, one would expect to have a shell surrounding the neutrons, which was made of this matter which is squeezed so hard that the electrons are flowing freely through it, as they do in a metal, and we call this degenerate matter. And this would be very, very dense, about 1 ton per cubic centimeter in here. As you go in further into the star, you'll run into the almost pure neutrons. And the remarkable prediction is that these neutrons would actually be a liquid. They'd be a very remarkable liquid, what we now call a quantum liquid. This is the kind of liquid which flows with no hindrance. It is a liquid without viscosity. And such liquids were, in fact, predicted by Einstein long ago. And it is delightful, really, that we can find them in bulk inside a neutron star here. And this is the material with roughly 100 million tons per cubic centimeter. If you want some idea of what 100 million tons per cubic centimeter means, it means roughly this. A teaspoonful of material would be sufficient to create 1,000 ocean liners.
Pues la estructura de una estrella de neutrones no es tan absolutamente simple, no son todos neutrones. En la parte exterior hay materia meramente degenerada, con meramente 1 tonelada por centímetro cúbico. Yendo hacia el centro se obtiene, hay presente los neutrones. Y la masa de la estrella es fluida, es un fluido de un tipo predicho por Einstein que tiene una ausencia absoluta de viscosidad y de resistencia eléctrica. Es un fluido notable y es increíble que aquí tienes toda una estrella hecha de este tipo de fluidos. Y para dar una idea de qué significa esta densidad, una cuchara de materia pesaría igual que, how many liners?
1,000.
1,000 barcos de línea en una cucharada de material, el peso equivalente.
We still don't really know what would happen at the very center of a neutron star, where the pressure is even higher, because we do not know enough about particle behavior from our physics experiments in the lab here on Earth. We cannot create conditions like this, and it is just simply, we simply have to guess what happens near the middle. But we could have a very strange material, like solid quarks, which are one of the fundamental particles.
Pues en el centro hay una zona que podría consistir en partículas que en la Tierra no se pueden ni siquiera crear en nuestros experimentos de físicas de altas energías, que llamamos quarks, y es posible que en el centro de la estrella de neutrones hay este corazón de los quarks. Eso es un poco especulativo.
The gravitational effects close to a neutron star must, of course, be enormous, because you have the mass of a complete star squeezed into the volume of a diameter of 20 kilometers. And just to give some illustration, neutron stars, if you wait long enough, they are completely inert objects. They are just simply cooling, if you like, the cooling ashes of a star, which have been highly compressed. And if the universe lasted long enough, it would be possible perhaps in the future with spacecraft to visit a neutron star and walk about on it, but it would not be very comfortable because if you take some nice light person like a ballerina dancer and put her on a neutron star, then she would weigh, I think, about 30 million tons.
Pues una estrella de neutrones de cierta forma es una cosa inerte porque realmente es cenizas de una estrella, no produce energía internamente y si tuviéramos tiempo suficiente, más o menos la edad del universo, podríamos esperar hasta que se enfríe, y ir y visitar y a aterrizar o a estrellizar en la superficie y allí, pero no estaríamos muy cómodos. Un bailarina pesa 30 millones de toneladas, hay una persona ligera, un poco pesada realmente.
Of course, she could never stand. She would squash flat very quickly, and you can just see her there. She'd be very thin. She'd be spread very thinly over the.
La pobre se aplastará.
More seriously, I think Einstein, and I must refer to him in this famous year, Einstein would really have loved pulsars and neutron stars because they provide a scenario in which some aspects of his theory of general relativity can really be tested in a major way. Conditions where his curvature of space-time and the fact that gravity affects clocks, it is a fact that if you put a clock near a heavy object, the clock begins to run more slowly. This is a fact of the space-time which is impossible to describe simply in a few words. Einstein's concept that gravity, the force of gravity, is due to, as it were, a bending of space and time. This effect is rather extreme, and if you put a clock on a neutron star, it would run about 2 hours slow each day.
Pues a Einstein le hubiera encantado las estrellas de neutrones porque ofrecen laboratorios para comprobar su teoría de relatividad general, oportunidades que no tenemos aquí en la Tierra. Su teoría implica que la masa causa la curvatura del espacio-tiempo, sin entrar en detalles, y como consecuencia que las estrellas cerca de cuerpos muy masivos corren más lentamente. Y en la superficie de una estrella de neutrones, un reloj pasaría más y más lento al ritmo de 2 horas por día. Es muy extremo.
Luckily, we can check some of these strange behaviors of a neutron star by direct experiment. And I'd like to come back now to the model I showed, where a neutron star had a very rigid outer crust and a liquid interior. We get real observational evidence that this must be the structure of a neutron star by a phenomenon which I show in a general way here. Because pulsars are such accurate clocks, if they change their rate by even a tiny amount, like 1 part in a million or 1 part in 100 million, this is an effect which can be measured. And it was observed in some pulsars that the pulse rate suddenly would jump by a small factor, less than 1 part in a million, but as I said, somewhere less than 1 part in a million. But a sudden increase of pulse rate was found in certain pulsars. It was found in the Crab Nebula, and it was also found in other pulsars visible in the southern sky. Shown schematically here, these sudden increases would happen perhaps once every 2 or 3 years in certain cases. And by careful timing, you can see that the pulse rate rises suddenly, and I do mean that within a day, it suddenly jumps, and then recovers somewhat slowly like this, and tries to come back to its original rate, but never quite succeeds. I should have mentioned before that the pulse rate is actually always slowing down, because the neutron star, spinning neutron star, is losing energy in various ways, and of course spin motion is all the energy it has. So when the pulsar loses energy into radiation or any other way, the pulsar must slow down, and this is observed.
Hay evidencia que se va a presentar sobre la estructura de un pulsar, que tiene esta corteza que se vio en el diagrama anterior, y va así, que el ritmo de los pulsos de un pulsar baja sistemáticamente con el tiempo, porque el pulsar pierde energía, entonces va cada vez más lento. Se puede medir con gran precisión este ritmo de pulsos, y en algunos pulsares, la nebulosa del Cangrejo, que es uno, y varios en el sur, se han medido un cambio abrupto en este ritmo de pulsos. Este cambio ocurre durante un periodo de horas o un día, y ocurre cada 2 años, 3 años, así. Y después el ritmo se aproxima al ritmo original. Este fenómeno se llama glitch, como se dice aquí.
Thank you. Now I'd just like to mention more about Einstein. Einstein revolutionized our ideas of space and time. And some of his ideas can be understood quite easily. And I think there are some facts of relativity theory which everybody should know and understand, and perhaps even be explained to other people. When I was lecturing on these things at Cambridge years ago, I used to say to my students, if you can't explain something about the theory of relativity to your historian or English literature friends, you don't really understand it yourself. So if you'll forgive me, I would just like to give you some examples of Einstein's basic thinking and how it immediately changes our ideas of space and time. Time is not the same for everybody. It cannot be, because it is a fact of observation that light always travels at the same speed. Whoever observes it, however they are moving, however the light is emitted, whatever its source, the speed of light is always the same. From this you can see immediately that events which are simultaneous to one person will not be simultaneous to another. Suppose you have a very simple experiment. You have a room with a flashing light in the middle, and the light flashes, and the light waves go off, and they will hit each wall at the same time, obviously, if they travel the same distance. But if you make that room move rapidly in one direction, what happens? Well, the speed of light is the same as you observe it from outside, and it's clear that that's where the light flash was emitted. The light pulse moves in equal times, the same distance from here, but the whole room is moving, so it must hit this wall before it hits that wall. So events, you might be turning on 2 television sets with your controllers in opposite directions, and if you're in a stationary room, television sets will come up together. But if somebody observes that from outside and you are moving very fast, one television set will come on, then another one. This is inevitable if you simply have a constant speed of light.
Pues es explicar en términos sencillos algunos conceptos de la relatividad. No voy a entrar en lo que dijo el profesor Hewish a sus estudiantes en Cambridge sobre el tema, simplemente decir lo siguiente. En estos diagramas, arriba hay una lámpara que emite un pulso de luz que va a la misma velocidad en ambas direcciones, porque la velocidad de la luz es constante, es un fundamento de la teoría. Y llega a ambos lados de la habitación en el mismo momento. Si en vez de estar en una habitación estacionaria, estás en un tren, entonces la luz no llega al mismo momento a ambas partes del tren. Y visto de fuera, cosas que parecen simultáneas en la habitación estacionaria aparecen ocurrir a tiempos diferentes en el tren, con lo cual la simultaneidad no es simultaneidad para todo el mundo, es diferente y es relativa a la simultaneidad.
And just one more very simple example, and then I will not try and teach you any more simple relativity, but it really is so fascinating if you think about it. A clock which moves must run more slowly than a clock which is static and stationary. And that is extremely easy to understand. Suppose you have a clock which is operated by a flashing light, and the light flashes, a pulse is emitted upwards, hits a mirror, and comes down. And suppose the clock simply goes tick-tock, 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 every time the light flash goes up and down. Now, put that clock on trucks which move very fast, and what happens? Here's your clock, the light flash is emitted. By the time the light flash reaches the upper mirror, as we see it from standing on the ground, not on the train, the mirror has moved to here. So it goes tick, tock. It has to run more slowly because the light has further to travel. It is traveling at the same speed for you as it is in the train. Clock time is slowed down.
Pues también el tiempo se ralentiza con el movimiento rápido y eso se ilustra. Si tienes un reloj que emite un pulso de luz que se refleja de este espejo, sube y baja, cada vez se emite, el reloj dice tic y después toc. Pues el tiempo tiene su valor aquí, el tiempo de tránsito. El mismo sistema en este tren, la distancia que se tiene que mover la luz es más grande, con lo cual, vista desde fuera del tren, el tiempo tiene que ser más largo porque la luz viaja siempre con una velocidad constante, con lo cual el resultado es que el reloj va más lento y eso es uniforme. Con velocidad más alta, más lentamente corre el reloj.
One of the predictions that Einstein made from his theory of curved spacetime, his theory of general relativity, is that under certain circumstances, gravitational waves could be created in much the same way as electromagnetic waves. In your mobile telephone, when you switch it on, electrons move rapidly up and down in the antenna, which is here, and they transmit radio waves, as you know. If you take two massive objects and rotate them, you get a similar effect in general relativity, and waves of gravity, waves of gravitational force are released, and you can call these what you like, ripples in his curved space-time, it doesn't matter, but what would be the effect of a gravity wave if it comes through a room and you are there, or if perhaps you are a hunter outside with your gun and a strong gravity wave goes past? Well, it's a force which will stretch you and squeeze you, or the opposite. And if you have a very strong gravitational wave, you might look like that for a moment, or you might look like that. And as the wave passes, that's what will happen.
El teléfono móvil emite ondas radio y lo hace porque los electrones suben y bajan muy rápidamente, oscilan rápidamente dentro de la antena o dentro del teléfono móvil. Por analogía, dos masas girando rápidamente alrededor de sí emiten ondas de gravedad. Esas ondas de gravedad pueden, si son fuertes, al pasar por un cuerpo, causan compresión y rarefacción. Una persona estaría así muy gorda y después muy flaco, muy rápidamente, por analogía, claramente. Es un poco exagerado por efecto.
These effects in real life are extremely difficult to measure, and no one has yet succeeded in detecting a gravitational wave of this kind. But the reason I said earlier that Einstein would have loved pulsars is that they enable the detection of gravity waves of this sort, although indirectly. And this is the last aspect of pulsars which I really shall mention now. It was in 1974, using this radio telescope. This is a famous radio telescope. It's 1,000 feet from side to side. This is simply a reflecting bowl. It exists in Arecibo in Puerto Rico, and it is just a giant radio telescope which reflects signals up to the collector at the center there. The radio waves falling into here get reflected to detectors up in the center. And with that radio telescope, two astronomers, Hulse and Taylor, working in the United States, discovered a most remarkable object, which was two neutron stars in orbit about each other. What we call a binary pulsar. The one neutron star cannot be detected. It's quite invisible, presumably because the pulsar beam is not pointing in the right direction, that we don't see it. But there's one over here which is a pulsar, a detectable pulsar, and what Einstein predicted in a system like this is that such a system will generate gravitational waves which will leave this system in all directions, and the system will simply lose energy. Now, that means that the orbit will begin to collapse. And this is an effect, because pulsars are such good clocks, that can be detected by the very precise orbital motion determination which the pulsars actually provide. These are measurements made by Taylor, and they show the effect of the collapse of that orbit due to the fact that it is losing energy. And the prediction that Einstein made is shown by the curve here, this black line here, this curve. That is Einstein's predicted effect on the orbit of that system. And you see observations here going from 1975 to the mid-1990s here. And the observations fit Einstein's prediction absolutely precisely. And this was really, if only Einstein had been alive to see this, this would have been an enormous triumph for him.
Las ondas de gravedad no se pueden detectar en la Tierra, pero sí se pueden detectar bajo las circunstancias apropiadas utilizando los pulsares. En el año 1974, dos radioastrónomos, Hulse y Taylor, utilizando el gran telescopio, radiotelescopio en Arecibo, en Puerto Rico, que tiene un diámetro de 300 metros, descubrieron un pulsar binario, que son dos estrellas de neutrones en órbita, una alrededor de la otra. Una siendo un pulsar, la otra no. En la realidad, probablemente ambas son pulsares, pero el haz de solamente uno se puede ver por nosotros. Utilizando medidas muy precisas de los pulsos, se puede medir el cambio lento de la órbita debido a la emisión de las ondas de gravedad. La predicción de Einstein es esta línea, y las medidas hechas durante un periodo de casi 20 años son estos puntos. la teoría, ten en cuenta que Einstein promulgó su teoría en el año 1915, la teoría predice precisamente las observaciones. Einstein hubiera estado absolutamente encantado con este resultado.
This is the last picture I will show you, and I show it because this is the most rapid pulsar which has yet been discovered. In all now, we have, from observations made in many different places over the world, a total of nearly 2,000 pulsars, and a number of them are in these binary orbits, which makes them extremely interesting objects. But this, the one I show you now, is the most rapid pulsar. We call it a millisecond pulsar because the interval between pulses here, as you see, it produces a flash from each end, as it were, of the neutron star. There's the main pulse and an interpulse, main pulse, interpulse. And that is going around so fast, it is spinning at over 600 revolutions per second. If you imagine a star as heavy as the Sun, in fact slightly heavier than the Sun, compressed to 20 kilometers, spinning at 600 revolutions per second, it's really an amazing idea. And this shows you just what pulsars can do. Now, as telescopes observe more and more pulsars, we're finding more and more of these interesting objects which can be used for tests of general relativity to very high accuracy. And there have been many different theories of gravitation since Einstein produced his famous paper. And of course, physics doesn't stand still. We can't expect necessarily that Einstein to be totally correct forever. But the answer so far is that all the other attempts to explain gravitation by slightly modified theories have failed, whereas Einstein's theory is now seen to be accurate, has been checked to much better than 1% in these very strange effects like emitting gravitational waves. As time goes on, we're finding more interesting pulsars to do further tests of gravitation. And for me, it's I've tried to give you some flavor of what research in pulsar physics, pulsar astronomy is all about. It's a great satisfaction to me that the work on pulsars now, so long after the discovery, still seems to be as exciting, if not more exciting, than it was 35 years ago. Thank you very much.
Voy a traducir sobre todo porque nos presenta, hay 2.000 pulsares aproximadamente ahora descubiertos. Este es el más rápido, que gira una vez cada 600 veces por segundo. Imagínate una estrella de la masa más masiva del Sol, del tamaño de Madrid, girando 600 veces por segundo en su eje. Es extraordinario. Y el profesor Hewish indica con gran satisfacción y seguramente con orgullo debido que su descubrimiento ha dado lugar a astrofísica, a pruebas de Einstein, a astrofísica en general, que sigue más interesante casi que nunca, que los pulsares han mostrado que la teoría de Einstein es la mejor teoría de gravedad que hay hasta el momento, no necesariamente para siempre, por supuesto, pero hasta el momento, y que le da una satisfacción enorme poder haber iniciado este gran periodo de descubrimiento.
Vamos a abrir, como todas las noches, un pequeño turno de preguntas.
Buenas noches. Yo quería preguntarle al profesor Hewish, dos preguntas en principio. ¿Cómo es posible que un pulsar, si está formado, digamos, su capa externa por material degenerado y por un superfluido que emita luz visible, es decir, emita fotones, se supone? Y en segundo lugar, es si todas las estrellas de neutrones tienen que ser pulsares, es decir, todas giran y tienen su momento angular y, en fin, todo eso.
Okay, so the first question was, how is it that if a neutron star has a degenerate crust and a superfluid core, that it can emit light, it can emit photons? That's the first one. And the question is whether all neutron stars should be pulsars.
The secret, that's a very good question, and we don't know all the answers to that yet. But the reason for the emission of radiation is due to the fact that all stars are magnetic, they're magnetized. The sun has a magnetic field. So far as we know, all stars will have magnetic fields. And so when they collapse to form neutrons, the magnetic field cannot escape, and the magnetic field is collapsed into a tiny volume. You end up with an enormously powerful surface magnetic field strength. And when you combine that with the concept that the thing is spinning very fast, you have an electrical system of immense power. You can generate enormous voltages in a spinning system of that sort. And it's been predicted theoretically, and it's almost unavoidable that you will find surrounding the neutron star a very extended atmosphere, which I show you here. This is a sketch of what the atmosphere around a neutron star might be like. It would be symmetrical more or less around the magnetic axis. So if you have a little neutron star in there with the magnetic axis this way, and the neutron star is rotating about perhaps a vertical axis, then acceleration of electrical particles can generate light, gamma radiation, radio waves, depending on what part of this atmosphere you're thinking about. There are many theories about how the thing will generate radiation. So you mustn't think of a neutron star as just a lump of material in isolation. Its surroundings will be highly determined by the precise angle of rotation, the precise magnetic field strength, but you cannot avoid really the fact that the electrical forces will be strong enough to pull charged particles from the surface, where you do have protons and electrons. And the moment they're clear of the surface, they will be accelerated in these enormously powerful fields. And you can get gamma radiation, and you can, in fact, in appropriate magnetic field configurations, generate radiation of all wavelengths. But I should stress that at radio wavelengths, we're dealing with something much more like a radio transmitter than just a hot gas. I mean, it's behaving a little bit like a laser to produce the signals. We need the coherent movement of charged particles to produce the radiation at the strength we observe. So,
bueno, la razón básicamente, son dos elementos que dan lugar a la emisión de radiación. Una es que después del colapso el campo magnético no se escapa, se comprime y se aumenta muchísimo. Y que también es un objeto que gira rápidamente, es un dínamo básicamente, un tipo de dínamo muy efectivo. Y que alrededor de la estrella hay una atmósfera similar a, bueno, es una atmósfera de plasma normal, es decir, que tiene electrones y protones. Y la combinación de campo magnético y rotación rápida da lugar a aceleración de partículas que a su vez da lugar a radiación. Eso ocurre básicamente en la atmósfera del pulsar, no en su interior. Los mecanismos, hay argumentos sobre los detalles, pero básicamente es así, inevitablemente así. Bueno, yo creo que he cubierto básicamente lo que se dice. Y la segunda parte fue, si todas las estrellas neutrinas son pulsars, are all neutron stars pulsars? Although you did answer that a bit, obviously, you need to say it again.
I think they must be. But of course there will be many neutron stars with the beams pointing in a direction which makes them undetectable.
Todas las estrellas sin neutrones deben ser pulsares, pero el ángulo, el haz es un haz, realmente, y si no estamos dentro de la línea que da el haz, no lo vamos a ver, es así. Whether pulsars always spin in the same direction or whether they can spin in an arbitrary direction.
Or they spin any direction, depending on the original star.
Sí, en cualquier dirección. No hay dirección fija con respecto al universo. Es una cosa aleatoria.
Buenas noches. Si el primer pulsar descubierto hubiera sido un pulsar binario, ¿le habría llevado eso a la conclusión de que era de origen artificial?
If the first pulsar you found had happened to have been a binary pulsar, would you then have come to the conclusion that it was an artificial source?
That's an extremely good question. I can't give you the answer because the situation didn't exist, but that would have been very difficult. I think I would have had to think much longer about that.
Of course, bueno, es una cuestión hipotética con la cual no puede haber una respuesta, una pregunta hipotética. Sin embargo, es una pregunta difícil. Dado que el pulsar binario tiene un periodo de 7 horas y eso implica que está muy cerca de su otra estrella, hubiera dado lugar a la conclusión que no era un planeta capaz de dar vida. Eso es, I think a binary pulsar has a period of 7 hours.
Yes, it would be very hot for life.
Yes. Sí, demasiado caliente de todas formas para vida.
Buenas noches. I have my question in English. With the basic concepts of the quarks, a proton being 2 ups and a down, and a neutron 2 downs and an up quark, as the protons are converted to neutrons, how does the quark theory enter into the liquid neutrons and the quark core?
This is a particle physics question which I think no one can answer at this minute because we simply don't know enough about the behavior of those elementary particles at such close range.
Okay, la pregunta era sobre los quark, dada la construcción de neutrones y protones de los quark, ¿cómo es posible que la estrella de neutrones tiene las propiedades que tiene? La respuesta obviamente que es una pregunta de física nuclear que no podemos responder porque no tenemos el laboratorio para comprobar estas cosas. Entonces es demasiado difícil en este momento responder.
Hola, buenas tardes. Quería preguntarle si alrededor de una estrella de neutrones se crea un espacio vacío como ocurre en un agujero negro y en qué medida o en qué se diferencia.
If around a neutron star there is an evacuated space, as he says, as there is around a black hole. And if in that case, how would one differentiate these two things?
I think conditions around a neutron star would be very different from a black hole. The point about a black hole is that you cannot get particles coming coming out of it except Hawking radiation, as far as I understand black holes. So they really are very different physical situations, and I don't think they're comparable really in any way.
Hay grandes diferencias. No es factible, no es posible el escape de partículas de un agujero negro, por ejemplo, para dar un ejemplo solamente, salvo la radiación de Hawking, con lo cual la situación aquí en un pulsar es muy diferente. Toda la luz y las partículas salen de ahí, es diferente.
¿Cómo es el fin de un pulsar? ¿Cuánto tiempo vive un pulsar y cómo acaba?
Okay, how long does the pulsar live and how does it end up?
Does it end up? Yes. Well, that's a very nice question. We know roughly how pulsars are losing energy, and if you look at the rate of slowdown of a pulsar, then we can make some rough estimate of how old the pulsar is. And in general, it seems that most pulsars are about 10 million years old. As pulsars become slower and slower, then the electrical effects get weaker and weaker. And I think ultimately they will simply lack the electrical voltages to generate the atmospheric effects, which you see on the slide here. And that will be really rather like turning off a transmitter. The radiation will no longer be emitted, and the pulsar will simply be spinning in space in an undetectable way. And I think the galaxy must contain far more pulsars that we cannot see simply because they've stopped to radiate. You see, a lifetime of 10 million years or so is quite short on an astronomical timescale. And so there must be many old pulsars simply spinning in space but not generating enough electrical energy to radiate.
Es posible estimar es una buena pregunta, es posible estimar la longitud de vida de un pulsar, porque con el ritmo de ralentización de los pulsos, es posible estimar cuándo nació y cuánta sería su vida, y una vida aproximada canónica sería de 10 millones de años. Al final no pasa nada dramático. ¿Qué pasa? Es que la velocidad decrece, el impulso eléctrico como un emisor de ondas radio también decrece, y poco a poco la emisión llega a máximas débiles y desaparece lentamente. Es muy probable que hay muchos más estrellas de neutrones que no se pueden ver porque ya se han apagado que las que se pueden ver a causa de este proceso de decaimiento lento en su emisión.